All right. Well, thank you everyone so much for joining us today. If you don't know me, my name is Jillian LeClaire and I work in the Florida Tech Office of Alumni Affairs here in Melbourne, Florida. And today we have an awesome lunch and learn lecture to explore the upcycling of organic components of municipal waste. And for this, I'm so excited to partner with Florida Tech faculty member, Dr. Toufiq Reza, to bring you this informative lecture. Dr. Reza's presentation will be about 45 minutes long with time reserved at the end for questions, but throughout the lecture, if you think of something, question, comment, please feel free to put that in the chat and we'll circle back to that at the end. My only request for everyone is that you leave your microphones on mute throughout the duration of Dr. Reza's lecture so that we don't have any audio feedback. That's very helpful. Thank you. And real quick, to get a better idea of who's joining us, I'm going to launch a quick poll just to let us know where you're coming from. We should have the Jeopardy music playing. All right, we're at 70% completed. Just waiting for a few more people to finish. All right, 5, 4, 3, 2, 1. Okay, I'm going to end the poll and go ahead and share the results with you. So it looks like we have the largest representation from the 80s. And then we also have 16% who are not alumni and are friends of Florida Tech. So thank you for joining us today as a part of our wider community. What area did you get your degree in? We have 40% from the engineering fields, 28% from science, 20% from business, and a few from liberal arts and aero, and some other, I'm assuming like math or something like that. So thank you all. Mostly we have some folks from the East Coast, which makes sense because it is our lunchtime. We have 25% from US Central, a few from the West Coast, and a few from international. I saw on the registrant list, we have some folks from the Caribbean, from Canada, from Iraq, and obviously from Africa. So that's amazing that we're able to connect from all around the world today. And have you attended a lunch and learn lecture before? 32% said this is your first one. So that's awesome. I love that people are still discovering this. 68% said they've attended a few and nobody has attended them all. But at the end of the presentation today, I'll share a link of our library of previously recorded events. And you're free to explore those and watch them at your leisure anytime. So moving on, I'm going to introduce today's presenter and buckle up for a lengthy list of accomplishments. Dr. Toufiq Reza is awesome. He's an assistant professor of chemical engineering for the Department of Biomedical and Chemical Engineering and Sciences at Florida Institute of Technology. He also leads the Biofuels Research Lab at Florida Tech with a primary research interest in thermochemical conversions of biomass and biowastes. His research has been funded by the National Science Foundation, the U.S. Department of Agriculture, the U.S. Agency for International Development, and the Sugarbush Foundation. He received his MS and Ph.D. in chemical engineering from the University of Nevada, Reno in 2011 and 2013, respectively. He has published 68 peer-reviewed journal articles, 5 patents, 2 book chapters, and more than 100 presentations. Dr. Reza was named to the Industrial and Engineering Chemistry Research 2021 class of influential researchers. In 2019, he received the Marvin E. and Andy White Research Award from Ohio University. Also in 2019, he was awarded the prestigious American Chemical Society Petroleum Research Fund New Doctoral Investigator Grant, tongue twister, aimed to develop sustainable solvents for refinery processes. Dr. Reza is a member of multiple scientific societies, including AICHE, ACS, and ASABE. He is an officer of the AICHE Environmental Division and co-chair of the technical section in water. He is also the secretary of PRS 707, Food and Organic Waste Management and Utilization at the ASABE. He is a section editor in Energy's Journal and has also edited 2 special editions of Biomass Conversion and Biorefinery Journal and Energy's Journal. Phew! And with that, I am honored to turn it over to Dr. Reza.
Well, thank you very much. Thank you. Let me share my screen for quick. Screen number 2. Start the presentation. Right. Well, I guess I can go ahead and get started. Thank you very much, Jillian, for the nice introduction, and thank you for inviting me. It is a pleasure. I have seen. I personally I couldn't do those polls by myself. I think I was not included, but I did attend a couple of them previously, and then I did actually listen to them offline asynchronously. So it was a great thing. I get to learn quite a lot. This is a diverse audience, and people do a lot of work actually. That's very interesting. So today's lecture, I'm going to be focusing on converting waste to energy and materials. I tried my best to make it not too technical, but if you are interested on more technical depth, please feel free to send me an email, or we can ask the question and answer later. So let's introduce our group first. So my research group, we work on 4 different areas. So we work with biomass, and the one we work with is we call the hydrothermal treatment. Let's see if I can grab a pen. That's my laser. There you go. So I have a hydrothermal treatment, and I do work with the nexus of food, water, energy. There was a big initiative from National Science Foundation, because those 3 are inherently correlated. So whenever we have a food, there's a competition for energy and water. So how can we combine them together and meet the need for the society? So this is one of the things, and this is the hydrothermal treatment is something that we are going to focus today. But beside that, I will not be talking about it today, but feel free to reach out to me if you want to learn more what we are doing. So my other part of research is I'm doing the gas storage. In that case, I'm very interested on carbon dioxide capture, both from the power plant flue gas or from the direct air capture. So this is going to be this is already a big movement from the Congress and from the US that we are focusing more towards the carbon capture from air. Air has about 0.4% or 0.04%, 400 ppm carbon dioxide. So if we can capture it from air, this is going to be a massive accomplishment, and we can utilize it. Beside carbon dioxide, one of my students is focusing on the hydrogen storage as well. Hydrogen, we are going to be a hydrogen economy. So at that point, we are going to need advanced material where we can store hydrogen safely. One of the biggest concern about hydrogen is it is explosive, and storing is very difficult. So we're working on that. In terms of water side of it, I do work mostly on wastewater. We're trying to develop different adsorbent material that can target emerging contaminants from water. I did a little project on wastewater quality monitoring, but not that much. In terms of the waste plastic, I like to start working on, and I am working on, we call the chemical recycling of plastic waste. Instead of going for the single stream plastic, we like to go for a very tricky one. Not for the PET, we like to go for the polyurethane, which is basically the mattress, the foam. What happened to your waste mattress? And if it is going to your landfill, it is going to occupy such volume because it is very bulky. So how do we chemically recycle polyurethane So this is one thing. Also nylon and this kind of polyamide. So how can we break the bonds and how can we actually recycle those? In terms of personnel, I have 6 PhD students currently working in my group, and I have 1 master's student, 5 undergraduate students at this point. A couple of undergraduate students are actually graduated and they found their jobs. So the job market is getting better. I think it was last year it was a little difficult, but this year it is much better. So as soon as they graduate, they get a job. In terms of funding agency, our research has been funded by the U.S. Department of Agriculture, the NSF through the Nexus of Food, Water, Energy Systems, the USAID, the Agency for International Development. This is a nice one to expose my research to a developing country. In this case, I'm collaborating with my partners in Bangladesh, and we are developing how the best way to convert or to upcycle their municipal solid waste problem. I've researched to work with American Chemical Society Petroleum Research Fund. We're not going to talk that about it. So it's basically how do we make a sustainable refinery adsorbent. So this is what we were working on. And the Sugarbush Foundation, they are funding us to develop a method to handle septic tank waste. So septic tank waste is very different than wastewater treatment. And I was telling Jillian that I try my best to leave those exotic waste out of this lunch session. I know a couple of you are having lunch, and I don't want to spoil your lunch. So I'll talk about municipal solid waste, but I do work with septic tank waste. I do work with sewage sludge. I do work with the animal manures as well. So they all have different niche but today we are going to focus on the municipal solid waste, organic fraction of municipal solid waste and food waste. Okay. So next slide. So the municipal solid waste, as you see, this is an example of California. Why California? Oops. And the why California, because I did have a project with California. That's why I have that that one. So let's see if it is. Wait, what happened to my? That's my slide. Interesting. I have some things. So I guess my animations are not working. That's technical glitches. But anyway, so the point being here is I have the organic waste, which is made of about 50% of the municipal solid waste. And there are some inners, there are plastics, there are recyclables. Okay. The problem with municipal solid waste is, let me just put this next slide. The problems with municipal solid waste is it is heterogeneous. If you think about my household waste from this week will be different than my household waste next week. So it is different. And when we are collecting it, it is going to be a very heterogeneous. An industry cannot be built based on a very heterogeneous changing substances. So it has to be something that needs to be very consistent so that we have a consistent product. It often comes with high water content. Usually the municipal solid waste have poor mechanical dewaterability, high ash content, low bulk density, low friability. We're going to come back to those later. And usually it is contaminated with organic and inorganic contaminants. So the point being, because it is heterogeneous, it is very difficult to have one solution for everything. There is no one process that would solve all the municipal solid waste problem. So our idea is one way to go, but there are other ideas that are developing these days. I'm not the only one working on municipal solid waste or organic waste. We have identified that this is a serious problem, and there are a lot of us. We are trying to propose various different solutions for this problem. So this is just one problem this is just one solution that we are going to propose today. So one solution would be, if I have municipal solid waste, we're going to have that either the Republic Service or the waste management, they're tracking it. we can do something we call the autoclave. There are this kind of, I'm going to come back to autoclave next slide, but there are this kind of large scale processes which would actually operate at 140 to 150 degrees Celsius, which would actually melt those plastics and have separated the large particles from the organic fractions. So the large particles can then go to the MRF. MRF is also known as Material Recovery Facility, where there are more than 300 of them are operated in the US. Basically, they are here to separate the recyclable. So the recyclable plastics, recyclable glasses, recyclable papers, that's something that we could do. So that we can recycle and reuse it, but there is evidently an organic fraction. So one way to handle it is to go through anaerobic digestion. We can produce biogas, and in the US, we can have biogas, which is carbon dioxide and methane. Then we can capture carbon dioxide and have what we call a renewable natural gas, which we can actually inject it to the natural gas pipeline or utilize it. So this is what we can do. But when we produce biogas, there is another side stream coming from anaerobic digestion. It is called digestate. So what we can do with digestate, there comes my research into hydrothermal processing, and this is one way we're dealing with it. So I am not inventing autoclave. This is already invented. Material recovery facilities are already there. Anaerobic digestion of organic waste has been established as well. So I am putting my research into solving the last piece of puzzle. So this is what we are going to do. But I'll try to explain these processes a little bit and then introduce my research. So the steam autoclave. So how it works is again we bring the bags of municipal solid waste. And then it can go through a shredder if needed. The process I'm going to show you next, it doesn't need to actually go through a shredder. Shredder is a very good idea to minimize the size of it, but it also adds to the cost. And then it would go into an autoclave. Autoclaves usually run with a saturated steam, pressure around 10 bars, and the temperature about 140 to 150 degrees Celsius. After that, we are going to collect the products, as you can see over here, and the water vaporizes because it is 150 degrees Celsius product coming out, and then we are going to separate it. We're going to separate it in two fractions, a couple of fractions over here. And then from the fraction side, we can actually use the different product for different application. I just got off a phone with a huge energy group last week, I guess, Dane, and he said that based on the UK technology, they are actually building 13 new plants for autoclave industry in the US. They're already building it, one in the state of New York, in New York City, and they plan to expand more than 50 in next decade. That is going to happen. So we're going to see a lot of these autoclave facilities coming in, and this would actually allow us to reduce the load from landfill and utilize this material for other applications. Okay, so this is one process that is located. This is a pilot plant located in the Department of Agricultural Research Station up at West Coast. This is the western areas, and this is a pilot scale. So as you can see that these are the trash is coming in, and then it would go through an autoclave over here, and then this is the slurry look like after autoclave. It doesn't look that pretty, but the product is amazing. So if you look into the product, they are collecting it in two different fractions. So you have a biogenic fraction. They call the MSW pulp. We work with that as well. And this is a non-biogenic fraction. This is, as you can see, this has a lot of metals, a lot of plastics, papers, etc. So we could actually utilize it for the MRF. So when we're talking about MRF, the material recovery or sorting, this is the current one that we have operating in the US. And these are operated by Republic Services, they're operated by the waste management. And this is basically, they're bringing on the recycle fraction that we throw, and then it would go through a couple of different processes. It is going through the air sorter, it is going through the eddy current, the heavy plastics would be separating out, the glasses would be separating out, and sheaves to make the corks, papers, and plastics separated out as well. At the end, there would be this kind of product would actually go and utilize the recycle, but there would also be some organic fractions coming out, which we could then feed into the autoclave again if needed. Okay. But now what should we do with the pulp? We could try to sell it, whether we sell it to Georgia Pacific, whether they can make some paper towels or tissue paper out of it, or we can use it on other uses. For example, we propose to use it for anaerobic digestion. If you're not familiar with anaerobic digestion, it is a very good process to break down the organic substances into, and this is a biological breakdown, it's the maximum temperature we're talking about 37 to 55 degrees Celsius, depending on the feedstock, but it is breaking down to carbon into methane and carbon dioxide. The basic principle of anaerobic digestion is over here. So we have a complex organic matter, and then the first we are going to break down those organic matter. If you think about a sugar, a glucose, we're going to break down the sugar into acid. So this process is called acetogenesis. We're going to make the volatile fatty acid, for example. We are going to make acetic acid. Then we are going to go through acetogenesis, where these acids would form, and then it would go through a methanogenesis, where the different kinds of bacteria would actually convert the acids into methane and carbon dioxide. Okay, so it is depending on what kind of feedstock, how much carbon we have. We can produce methane and carbon dioxide, and I'm not going to show you the results today. We're still working on it, but we are trying to look for a way to capture carbon dioxide from biogas, so that we have, first of all, the carbon capture from the biogas. Also, we have a renewable renewable natural gas that can be used. So that's that. When we look into how the USDA pilot the anaerobic digestion system, as you see, we have the MSW pulp coming in, and this is less than 3/8 inch grid, and then it would go into the receiving slope, and then there would be the reaction zone, and then there would be that touch growth zone. This is how it would look like, and it works great. It works great, and this is some of the results. So this is Dr. Diana Franke. So she was a postdoc at that time. Now she left USDA, and now she's working in a company at Atlanta. Anyway, so this is what it looked like, and this is the solid product. So we're going to make biogas, and then we can utilize the biogas, but inevitably we are going to make the digestate as well. And if we look into the mass and water balance, if you remember your engineering part, as we are chemical engineers, we love doing our material and energy balance. So this is our bread and butter. So anything comes in has to go out. So that's the thing. So if you look into the anaerobic digestion from their USDA's pilot plant facility, for the 4,689 pounds of wet pulp, we need to add some water to facilitate the pumping. We are going to have about 157,000 liters of methane, and there would be another 40% would be carbon dioxide. But there would be another 3,000 pounds of wet digestate as well. And the USDA came to us and say, what can we do with the digestate? And there brings us to the technology that we are working on, what to do with the digestate. So that's our hydrothermal carbonization process. So this is a little bit new, so I'm going to go a little deeper. Because it is our process, I'm very proud of that. And also it is a little bit new for probably many of you. So to look into the hydrothermal processes, one thing we need to look into is the water. So the thermodynamic properties of water is specifically water at high temperature, high pressure. So my good colleague in University of Hohenheim, Dr. Andrea Cruz, she wrote a good paper, Water as Magic Solvent for Biomass Conversion. That is in 2015. I still refer her. What it means that when we look into the thermodynamic properties of water, here I have listed the temperature with the density, dielectric constant, and my ionic product. As you see, when temperature goes beyond 100 degrees Celsius, water would start to boil. What if I put the lid on? If I put the lid on, that water in vapor space is going to make the vapor pressure. If the vapor pressure is inserted, it would actually not allow the water to become a gas. The water would become what we call a subcritical liquid. Okay. And then if it reaches beyond its critical point, so water's critical point is 373 degrees Celsius at 22.4 megapascal. If you are familiar with PSI, it would be around 3,400 PSI. So after that, it is going to be a single phase. We are going to have a supercritical water. But what we found out that, and this has been reported earlier as well, if we go into the subcritical water, we see an order of magnitude increase of ionic product. And what is happening is the water is becoming hydronium ion and hydroxide ion. And this is the product of it is actually the ionic product. And what it means that in the subcritical water, I have a lot of ion, and those are subcritical water is acting like a mild acid and a mild base at the same time. So it is very reactive. The other thing we noticed that the dielectric constant decreases significantly. Now for water, dielectric constant is important because water at ambient condition is polar, and it is very benign. But the water at subcritical condition is actually starting to behave like a non-polar solvent. So, for example, water around 230 degrees Celsius would have the same solvation property as benzene. So it can actually dissolve that the other hydrocarbons as well. So the long story short, water at subcritical condition is very reactive, and it has a good solvation property. And we said that, okay, so we don't have to dry our feedstock. We can just use this water's property. We don't have to use any acids or bases or other harsh chemicals. We can just use temperature and pressure to convert this kind of wet feedstock into other materials. And this is what a hydrothermal carbonization process is about. So when we talk about the hydrothermal treatment processes, there are three usual processes, and depending on what we want. So it depends on the temperature, as we see that the water's critical point. And this is our famous phase diagram for water, if you recall. So in the phase diagram for water, the critical point is 373 degrees Celsius. So if we maintain our temperature between 180 to 260 degrees Celsius, we see a lot of a carbon formation, a solid carbon formation. So that's what we call hydrothermal carbonization, if my desired product is indeed the solid. But if we go beyond 260 degrees Celsius, beyond 260, but before the critical point, we started to see more of a liquid product. So this is called the hydrothermal liquefaction. There are several technologies they are developing around in Japan, in Europe, and in the US as well, where we are trying to hydrothermally liquefy solid waste, the sewage sludge, and try to upgrade that oil into a liquid fuel. And in this case, we are going to say it is a sustainable aviation fuel, and it did work. So I'm not going to go, this is another part of study. I'm not going to go into that. So we're going to focus on hydrothermal carbonization. But if you look into what happened after the critical point, the biomass, it would actually started to become gas. And in this case, depending on what catalyst we use, we can have either carbon dioxide, or if it is nickel catalyst, we could actually started to find a lot of hydrogen as well. So if your goal is to produce hydrogen, and if you are okay with 22.4 megapascal pressure and 400 degrees Celsius, the reaction is very quick, and it usually happens. But there are several issues. For example, at that supercritical condition, if there is any, if you have good amount, not a good amount, if you have any amount of halogens, it started to corrode very, very quickly. So this is one thing we have found. Anyway, in terms of reactions, I'm going to skip it very quickly, but this is on your side, the shaded side. We have the liquid and I have the vapor phase. If I have the vapor phase, I'm going to have a gas phase reforming and pyrolysis that you might be more familiar with. But in the liquid side, I would have dehydration, hydrolysis, the aqueous phase reforming, and all the way to the gasification. Okay. Now, what are the advantages of hydrothermal carbonization if you're talking about a solid product? So the hydrothermal carbonization is a wet process. We don't have to dry the biomass. And this is very advantageous for us because usually this kind of solid waste can have, the wet waste can have more than 95% of water. Evaporating it or drying it off is an extremely energy intensive process. So we don't have to do that. It can accept numerous biomass types. So we can have only one reactor setup, and then we can have different biomass coming in. One of my research is try to look into, we call the co-hydrothermal carbonization, where we actually blend the different biomass together and see how it affects with each other. It can also convert waste to energy and materials, and I'll try to cover both of them. Let's see how I do with the time. It is a non-catalytic process. So water itself, because of the thermodynamic properties of water, we are going to utilize it. We don't have to use catalytic process, but there are technologies which are nowadays which are building as a catalytic hydrothermal liquefaction or catalytic hydrothermal carbonization if we want to make a final product out of it. But there are other issues as well, how to recycle the catalyst, how to regenerate the catalyst. Depending on what we have, we found that the reaction is slightly exothermic. Now, it is slightly exothermic is a good thing. Too exothermic means that I am, in chemical engineering, we are very, we call the runaway reaction. So anything that is combustible, we have to design that runaway reaction, make sure that everything is cooled down for the process safety perspective. Slightly exothermic, this is good. The exothermic means that the reaction itself is a heat producing. So if we can make that process in such a way that we are utilizing the heat effectively, there is a possibility that we probably don't need to add enough heat or additional heat when the process is running at a steady state. Again, it's a straightforward process, and usually the product that I will show you next, it is hydrophobic. That would usually ease on filtering if your goal is to separate water afterward. Again, as I'm saying, this hydrothermal carbonization process is basically a pressure cooker. So this is all I'm saying in a very technical way, but this is basically what I'm saying. It's a pressure cooker. You put everything, you remember, I put my meat and everything and put the lid on and then have a weight to it and then cook it. And we know that pressure cooker cooks it faster. And I know why, because it is pressurized. So we just go beyond that. I mean, we have a couple of fancy, if you can think of pressure cooker, which could go up until 500 degrees Celsius, 5,000 PSI. Little more robust, little more controllable. In terms of the temperature wise that we already talked about, it is about 180 to 260, 280 degrees Celsius. Depending on what we want, the residence time can vary from 1 minute to 12 hours. The higher the temperature, the lower the residence time. As you remember, the kinetics. So the kinetic works in this way. The higher the temperature, the lower the residence time. And we do not add any pressure. This is an autogenous pressure during the reaction. So what we go through the biomass, in this case, it would be digestate, and biomass already would have water. There are a couple of products coming out. There will be a solid char coming out. So this is what we call the hydrotherm. This is how it looked like. It's black, it's dark. But there would be some gases coming out, probably around 5% of the carbon would convert it to gas. One of the reaction for the hydrothermal reaction is a decarboxylation, where we could see some carbon dioxide coming out. We'll have water in platform chemicals, in sugars and acids. That is another product or byproduct that we are looking into it as well. Okay. Just go a little more into it, and I'm not going to spend too much time on it, but this is to construct this reaction mechanism. It costs us several groups for more than 6 years to actually construct it into how it is happening. In a nutshell, we have that the biomass would actually go into hydrolysis, where water will be consumed. It is going to break it down to different monomers, which would then go into dehydration, to go into a couple of other reactions we call the condensation, polymerization, aromatization. And in every cases, we are going to see some dehydration product coming out, and also some decarboxylation product coming out. So altogether, we start with the biomass, which will come up with a more carbonated, defined product that would end with. Slide. Right. So if we look into hydrothermal, and this is how it would look like chemically. So we usually have a hydrophobic core, and we usually have a hydrophilic shell. And this is a hydrophilic, it's more into, we have more functional groups. And when I see you, the material property or material application of this kind of solid char, the functionality is a very big factor for this one. But in terms of fuel, I would need a lot of carbon and a lot of hydrogen, because those are the ones which would actually reflect my my fuel value. Next slide. So now let's come into the application finally. So what can we do with it? Okay. So in terms of application, if I want to make a good solid fuel, there are a couple of things I need to do. My good solid fuel should have a high energy density. Unfortunately, biomass doesn't have a good high energy density. It is very light. It should have a good grindability. I should press it very quickly, because if I want to use it in an existing power plant or a boiler, it has to be very fine so that we can burn it very quickly. It's better for we have hydrophobicity, or we increase the hydrophobicity, because the more it's hydrophobic, the better the storage ability would be. Okay. We want to maintain a high but uniform burnout temperature. So when we want to burn it, we want it to be burned at a very narrow temperature range, and we want it to burn very efficiently as well. So last thing we want is, we're going to set it up with a co-feeding. For example, I have two different feeds. I'm going to feed with coal. I'm going to feed with natural gas with this product, and then they too will burn at separate temperatures. So that would be not feasible. I would want low ash, because I don't want to handle too much bottom ash or fly ash. I would like to have the fuel with very low halogen compounds, because we want to avoid corrosion. And of course, we have to compete with the price of fossil fuel, price of coal, and price of natural gas. Okay, now how are we doing with that? So first, take a look at the pictures of the hydrothermal from digestate, and this is from the digestate hydrothermal over here, and this I have. Where is my cursor? Okay, and this I have some digestate from that before it went through the the anaerobic digestion. Now, what kind of fuel we're making? So we can do elemental analysis, and then we can draw something we call a Van Crevling diagram. So this is basically plotting the atomic oxygen-carbon ratio with atomic hydrogen-carbon ratio. Again, my ideal fuel will have a very low oxygen and very high hydrogen to carbon ratio. So that means if I have a very good fuel, I should expect it to be very close to the origin. The farther it goes through origin, from origin, the bad the fuel value it would be. And we see that biomass is actually a very far away. So once we do the hydrothermal treatment, we are actually bringing that one all the way to a coal region. So it is from that elemental analysis, we see that we are making a product similar to coal. Very nice. How does it grind? So from here, you see that the raw biomass, it doesn't grind really well. So we can put it into the grinder. We put a similar amount of power to grind it, and you see most of it's more than 425 micrometers. So it doesn't really grind well. But with hydrothermal treatment, we started to see more and more fine powder. So it would actually take less energy to grind it. Now let's talk about the mass and energy densification. Here we did put together something we call the single press pellet press, how it would actually densify. And these are some of the results we see over here. So this is my mass density. It's basically, I have a cylindrical pellet. I know the volume and I know the mass. So mass divided by volume, I have mass density. And this is my true density, not my bulk density. And we see that my mass density increases from raw to the hydrochar over here. And so as my energy density. Energy density is basically, I multiply it with the higher heating value or energy content of the product. So I could see that my energy value is increases, my energy density has increases, and I have my grindability increases as well. Now let's take a look at the hydrophobicity. So how do we measure hydrophobicity? And this is something we call the contact angle measurement over here. So if you put a droplet of water on a surface and you measure this angle from here to here, this is what we call a contact angle. If my surface is super hydrophobic, I should have my contact angle between 150 to 180 degrees Celsius. So you can look into, put a droplet in polyethylene, and polyethylene is super hydrophobic. So you would see that it is actually holding its shape and the contact angle is really, really high. But if you put the same droplet in a paper towel, you're going to see that it is going to be a super hydrophilic or hydrophilic, depending on how long you're going to stay. So based on that, we see that if it is hydrophobic, this is our target. We can go up until 90 degrees to 150 degrees Celsius. And this is the result we are finding. So this is where we see that water droplet with time. So we waited, we put a water droplet in those, the pellets, and wait a couple of minutes. And we see that there are a little bit of water is actually, the water droplet diameter is actually increasing. That means water is going. And that time, our contact angle is decreasing as well. But eventually, my contact angle is steadied at between 100 and 110 degrees. That means we are talking about a hydrophobic surface, and that is encouraging for us. Now, so I have a hydrophobic material, and I have a good grindable material, and it has good energy density. The question is, how does it burn? We put our samples in a thermogravimetric analysis, and these are the results. As you see, if we have only food waste, it started to burn much early in air atmosphere. And the food waste, you see, the most of it burned around between 200 and 300 degrees Celsius, where I have my bituminous coal that would burn between 500 and 600 degrees Celsius. So if we want to do a co-feeding, I do not want to mix the raw food waste with my coal, because if I mix it, And then if I put it into a boiler, it's going to, all the food waste will be burned first, and then it will burn the coal. But if we do a hydrothermal treatment, our hydrothermal, we see that this actually burns more similar to coal. So that's an encouraging thing for us. Now, we haven't talked about that. So this is like what happened to our process liquid. This is what we are still working on it. But we found that our process liquid, depending on what kind of feedstock we use, it can have high amount of total organic content, and it will have a good high amount of total nitrogen. So if I have a lot of nitrogen containing feedstock, a lot of protein, I could end up a good amount of nitrogen that is in the process liquid. Now, a good amount of nitrogen is a good thing for process liquid if we want to make it as a nutrient recovery side of it. This is what we're working on. Or if we want to do it as feed it to anaerobic digestion, see whether they can further break it down. So these are a couple of researches currently going on that I should be able to tell you more probably a year or so. But in terms of the inorganic leaching from biomass, we see we do not have that much of halogens, but in terms of others, we see good amount of calcium, good amount of iron that is still remains on the hydrothermal. One relevant thing we studied is it might not be that relevant to our the municipal solid waste, but it is about the sewage sludge or dairy manure, if we are thinking about. So different kinds of hormones and antibiotics, what would happen to them? And we found that this is the estradiol, which is basically an active ingredient of the birth control pill. So if it remains there, the hydrothermal treatment would actually try to degrade it. And with the presence of glucose, the acidity, we can go up until 97% of degradation. In terms of oxytetracycline, a very common antibiotic, we could see about 70 to 90% of degradation. So this is encouraging, might not be relevant to municipal solid waste, but it is relevant. Now, the question is, I think I'm running out of time. I'm going to try to go a little fast. So the question is, it's a big question, how much would it cost? So we did, and this is a study, we did it for Ohio Coal Development Office, and they wanted us to test this, this technology to see whether we can actually co-feed coal waste and food waste together in a conventional power plant. So this is a conceptual, the process design over here with the continuous process design. And we have designed it, our reaction temperature was 260 degrees Celsius, and we are trying to separate the nutrients out of it as well. And we have tested in two different scenarios where we could do a coal, the process at a coal mine site where I have the coal waste, or we can do it at a power plant site. And in terms of both cases, the selling price was about $72 to $77 per ton. Remember, the coal, the bituminous coal is actually sold around like $55 to $70 per ton. So we are making good progress, but we still need to go somewhere. But in terms of if we increase the plant size, we actually see that the break-even cost is getting lower, and we could go up until about $50, but our hydrogen production on the plant size need to be higher. The plant size could be higher. The problem is whether we will have enough food waste to work with, and we will have to deal with the larger capital investment. So this is something that we need to actually, not with a funding agency and companies like Hughes Energy would actually need to consider. We did the sensitivity analysis, and we found that there are several parameters, including the price of the feedstock is very sensitive to our economics, so as the travel distance. And this is an enormous thing, like how far food waste can travel. So this is, and how far the product needs to be traveled as well. So this is something we are looking into it and see where it goes. Right. So this is my well, let's say it's 12:50. So I have a couple of slides and then I am going to stop. Jillian, I'm very sorry. I'm running out of time. So beside the waste, as you see, we are making good solid fuel. But beside that, one of our goal is to look into the adsorbent material. And here we are looking into different kinds of adsorbent material. One of our project is looking into absorbing harmful algal bloom. And the other project, we are looking into the hydrogen storage. So I'm going to skip this whole part and then look into what our next plan is. So hydrogen storage, it really works. So I wish I had enough time. Okay, so, all right. So the ongoing works, I'm going to spend like another 2 minutes and then I'll probably stop. So the ongoing works, one of the things we want to use it as this kind of hydrothermal process as an adsorbent material for direct air capture carbon dioxide. So this is a very complex diagram, and this is what we really plan on doing it. And after we capture the carbon dioxide, I want to collaborate with my colleagues from Ohio State University. So they are synthetically manufacturing microorganisms which would take carbon dioxide and sugars and make high-value chemicals, for example, ethylene and some other chemicals that can be done. So this is what we are working on. Hopefully, next time we can give you more update on that. The other thing we are working on, we just got the funding from USDA to look into this kind of hydrothermal process to mitigate nutrient pollution from the animal waste and also capture harmful algal bloom from water as well. So we are going to work on that. The preliminary results are very encouraging. So anyway, I get to conclude now. I'm sorry, I took a little more time. So the conclusion was biowaste is a huge source of energy and material. When I see biowaste, I don't see a problem. I see a challenge that we can solve, and it is a huge resource for us. It is available everywhere. But the problems, again, it is heterogeneous, it is moisture, it is unstable. To my opinion, we cannot have only one process, magic process would solve all sorts of biowaste problem. We have to go through a multi-step processing. So we have to work hands on hands with other existing facilities and new facilities and work together to find a solution that is relevant to the specific waste. And we see that the fuel characteristics of hydrogen, they're comparable to coal, but the processing cost might need to be considered. And this is what we didn't talk about, but we did. We are working on the hydrogen storage as of this material, and it is working. So probably next time I'll have more results. In terms of acknowledgement, I would like to acknowledge the funding agencies and my collaborators. And my wonderful undergraduate and graduate students, and thank you everyone for attending us. This is my research group website, and this is my email address. Please feel free to send me an email if you want to learn in detail about that. Thank you very much, Jillian. I'm so sorry I ran out of time.
Please don't worry, Toufiq. It was so informative. Everyone really enjoys the information that you're providing, and we'd rather have more content from you and optimize that time. So appreciate everything that you had to share. Very thorough. And what you said at the end about not seeing the municipal solid waste and bio-waste as a problem. I am so happy that we have people like you, because I see the problem and I am overwhelmed. So I appreciate all the research you're doing to turn it into something useful for us. So I just allowed you guys to unmute yourselves if you want to ask a question in person, or feel free to.
There are a few questions, Julian, in the chat box, so I'm going to probably go through it. And in the meantime, please feel free to unmute yourself and ask the questions. So the first question from Kelly is, when the water vapor pollute the air? yes, the water vapor pollutes the air, and the idea over here is we have to have that the air purifier. Every chemical plant, we have to have those kind of like a bag filter or filtration unit that we need to set it up so that we can capture the dioxins or this kind of thing. Good thing about this process is we don't pollute, we don't make those dioxins. That is actually a huge greenhouse gas emitter and responsible for that. So we don't pollute that. So that's one good thing in compared to pyrolysis, which would actually produce this kind of dioxins. So yes, it would be, but the industrial solutions are there. Now, the second question I have, it is more of a comment from Steve Kaysen. I would like to see more future presentations in plastic waste, specifically on nylons. Yes, we are working on it, and the results are very good. So our idea is, instead of not going to water route, plastic waste are usually dry. So what we are trying to see, can we use a different solvent, the solvent that can be readily available in refinery, and use it to actually chemically recycle the plastic waste. But yeah, I mean, it would be it would be next time. And then the Amr, I would love to find out more about the chemical recycling of polyurethane. Yes, we are going to do that, and capturing carbon dioxide from flue gas and at power plant. Yes, so this is something we are working on it, and the preliminary study is good. What we need to do in this case is we have to, because we are capturing carbon dioxide or we are capturing hydrogen, the gas capture, we have to make our material is highly porous. So we have to go through another step to make it a more porous material. We call the chemical activation. So we have to go through it, but then it works. Currently, I'm working with a couple of other faculties at FIT who are helping me out with this kind of like a direct air capture system and what to do with that captured air. I'm going to skip a couple of them. Thank you very much. I really appreciate it. Okay, is there a recorded version of the presentation somewhere? So I think, Jillian, that question is for you.
Yep, so we are recording the lecture today, and once Zoom sends me the link to the recording, I'm going to forward it to everyone who registered today, because I know there are some folks who weren't able to join us live. And then also, I just posted the link in the chat box where we keep all of our past Lunch and Learn lectures. So this recording will be up there in about a week's time.
Yeah. All right. So Kelly asked a very good question. So it is a wonderful question. Would you have to expand a lot of energy to heat the water? Yes, because our temperature is 260 degrees Celsius. We need to, but as a chemical engineer, we know that if we can recycle, or if we have a very good heat exchanger, and the heat exchanger I am looking into, we can actually preheat the stream and utilize about 80% of the heat from product to stream. So the way heat exchanger works is I'm going to pass my product in one side, and I'm going to pass my feed on the other side, and it is going to exchange the heat. So you're absolutely right. We need to increase the temperature, but commercially, what we would use is we would use a heat exchanger that would preheat the stream, and all we need to do is to heat the stream from to increase the temperature for 20 to 30 degrees Celsius in a steady state. It's a very technical question, but I really appreciate the question.
Kelly has great questions. All right, it looks like we hit our time at 1 o'clock, and we want to be respectful of everyone's lunch hour. So once again, I want to thank you, Toufiq, for taking the time to put together this presentation for us, and then also to give us this great lecture. And thank you to everyone for joining us. And I hope to see you at a future Lunch and Learn lecture or other virtual alumni events soon. Thank you, everyone.
Have a good day.
You too. Thanks.